Hey guys, it's time to work some examples. Alright, so first things first. Here we have a reaction, which is carbon tetrachloride decomposing into solid carbon and chlorine gas. And we have our corresponding delta H and delta S value. Now let me first ask you some questions about that delta H, because you can answer some stuff based off of your signs, and this is where we're getting into, so let's go ahead and talk about it. Alright, let's go to our piece of paper here. Delta H can be negative or positive, right? When delta H is negative, we say that it's exothermic, which means energy is released. And what do you think about spontaneity? Would this be spontaneous? And the answer is yes, we would imagine this to be spontaneous. Okay, let's look at positive. If it's positive, then that means it's endothermic, which means energy is absorbed to happen, which means we would imagine this wouldn't be non-spontaneous. Okay, so when I ask you the question, is delta H favorable, this would be the favorable one. Okay, this is what we would call unfavorable because it requires energy and it's not good. It doesn't lead to a spontaneous reaction. All right, what about delta S? Delta S can be negative or positive, right? When delta S is negative, this means entropy is decreased, which means it's a more ordered system. So this would be non-spontaneous. And another way to say this would be unfavorable. All right? Whereas positive means entropy is increased, which means it's a more disordered system, which means it's spontaneous and favorable. All right, so what's favorable then? A negative delta H and a positive delta S. That is favorable. All right, so let's look at what we got here in this question. That delta H is positive. That's not favorable. That says it's going to be non-spontaneous. But the delta S is positive, which says it is going to be spontaneous. Whenever you're getting two different stories, that's when the temperature matters. Whenever you're getting two different stories, that's when the temperature can change the spontaneity. Hey, if delta H is negative and delta S is positive, they're both telling you it's going to be spontaneous. Temperature doesn't matter. It's always going to be spontaneous. If delta H is positive and delta S is negative, they're both telling you it's going to be non-spontaneous. I don't care what the temperature is. It's going to be non-spontaneous, right? But in this case, you're getting two different stories. So we got to check it out. All right, we got to check it out. So let's go to our handy dandy piece of paper. All right, so delta G equals delta H minus T delta S. Delta H is 95.7 kilojoules minus T. Your temperature must be in Kelvin, so not 25 degrees Celsius, but 298 Kelvin, right? Times. So this was 25 degrees Celsius plus 273. Okay? Plus, go back to your delta S in the slide. Your delta S is in joule per Kelvin. What's delta H in? Kilojoules. So you don't need to write that as 142.2. That should be 0.1422. You got to convert that to kilojoules, right? So 0.1422 kilojoules per Kelvin. Okay, so to get that, we took 142.2 joule per Kelvin and we divided by 1,000. Okay? All right, cool. So now we just need to put that into our calculator. So we have 95.7 minus 298 times 0.1422. And I get a positive 53.3 kilojoules. Or if you write it as 53.3 kilojoules per mole, I'll still take it. All right, but that's positive. Positive delta G means non-spontaneous in the forward. So let's think about it. I mean, this makes sense, right? Delta H said it was going to be non-spontaneous. Delta S said it was going to be spontaneous. But delta S has a much smaller effect than delta H does, right? Because delta S is in a joule, delta H is in kilojoules. But you're multiplying delta S by the temperature. So here's the deal. If the temperature is cranked up enough, then it should become spontaneous, right? But we need a really high temperature to make this thing spontaneous. So let's look at that. All right, so how are we going to figure that out? Because that's the next question, right? The next question on the slide, which, sorry, can you go back? The next question on the slide is, for the reaction above, what's the minimum temperature that it will be spontaneous at? All right, well, think about it from a delta G perspective. Positive delta G is non-spontaneous. Negative delta G is spontaneous. So a 0 delta G is when it flips, and we want the minimum temperature. Okay, so if we want the minimum temperature, then we're going to say delta G is 0. Right? Now, delta H is delta H. That's 95.7 kilojoules minus the temperature is our X. That's the variable we're solving for. And then delta S, 0.1422 kilojoule per Kelvin. Okay, so we do some algebra. This becomes negative 95.7 kilojoules is equal to negative 0.1422 kilojoule per Kelvin times X. So then you divide both sides by the negative 0.1422. And we're going to end up with Kelvin as our unit. Okay? So put that in your calculator. Negative 95.7 divided by negative 0.1422. And we get 673 Kelvin. X equals 673 Kelvin. And that is exactly what the slide says. And you can check your work by plugging in 673 into where 298 was before and seeing what you get. So if I take 95.7 minus 673 times 0.1422, I get a negative 6 times 10 to the negative 4th. We have made this reaction spontaneous, but look at that temperature increase. Wow, oh wow, right? Not talking about shrimps here. We're talking about a pretty big temperature increase. Okay, so that's what we're saying, man. I mean, it matters, right? But now again, if they both are telling you it's going to be spontaneous, if delta H is negative and delta S is positive, I don't care what you do as far as temperature is concerned, it's always spontaneous. Or if delta S is positive and delta S is negative, they're both saying it's non-spontaneous. Again, I don't care what you do as far as temperature is concerned, that's non-spontaneous. So basically, what are we saying? When the signs differ, temperature doesn't matter, right? When the signs differ, temperature doesn't matter. But when the signs are the same, that's when you're getting two different stories and the temperature matters. Well, what do you notice? Who always wins at lower temperatures? At low temps, you abide by what delta H says. Okay, at low temps, you abide by what delta H says. But at high temps, that's when delta S wins. Okay, but delta S can only win at extremely high temperatures. Okay, so at low temps, delta S wins. At high temps, at low temps, said that wrong. At low temps, delta H wins. What it says goes. At high temps, delta S wins. What it says goes. And let's go to some examples. So which statement is true regarding the sublimation of dry ice. All right, sublimation. What's sublimation? It's phase change. Going from solid to gas. So solid to gas. Let's work our way through. All right. If it's going from solid to gas, are you breaking attractions or forming them? So we're going from less freedom to more, which means we must be breaking attractions. If we are breaking attractions, then delta H must be positive. We have to put energy in, which means B and C are out. They cannot be correct. B and C cannot be correct. All right. But if we're going from a solid to a gas, that means we've dramatically increased the entropy, right? Which means delta S has to be positive. Which means we know that it's got to be A. Right? It's got to be A. And since they have the same sign, that means that temperature is going to matter. At low temps, delta H is going to decide the spontaneity. And delta H says it's not. So it's not going to be spontaneous, and it's going to have a positive delta G at low temperatures. But at high temperatures, delta S gets to decide. And a positive delta S means it's spontaneous, which means delta G is going to be negative at high temperatures. Well, let's do one more question. All right, so here we have the Haber process for the production of ammonia. All right, and it's nitrogen gas plus 3 moles of hydrogen gas goes to make 2 moles of ammonia. They tell you that the delta H is negative 92.38 kilojoules. That means that energetically this is favorable. It's spontaneous from an enthalpy perspective. But delta S is negative 198.4 joule per Kelvin at 25 degrees Celsius. And that makes sense, right? I would predict a negative here because you're going from 4 moles to 2. You've decreased the entropy. This is not favorable. Okay? So at low temperatures, delta H wins, right? When you have the same signs. So at low temperatures, this is going to be spontaneous because delta H says so, right? But as you crank up that temperature, what's going to happen? Delta S is going to start winning, which means that negative delta G is going to start getting more positive, right? Hey, stop fighting. All right. Okay, so now let's do some math. So we're going to calculate delta G naught, or delta G. Ignore the degree symbol. We'll talk about the degree symbol later. Sorry about that. Calculate delta G for the reaction at 25 degrees Celsius and 500 degrees Celsius. So, delta G equals delta H minus T delta S. So delta H is always going to be negative 92.38 kilojoules minus, I'm going to start out with the 25 degrees Celsius, which is going to be 298 Kelvin, times negative 0.1984. Why? Because we divided by 1,000 to get it into kilojoules per Kelvin. Okay? All right, so if I put that into my calculator, so negative 92.38 minus 298 times negative 0.1984, I get that at 25 degrees Celsius, delta G is equal to negative 33.3 kilojoules. All right. Now, if this was on a test, I wouldn't expect you to show your work again. You could just change a number in your calculator, right? So what about at 500 degrees Celsius? I'm just going to go back into my calculator, and instead of writing 298, 500 plus 273, right, is 773. So I'm going to replace the 298 with 773. Okay? And I get basically a positive, now, 61 kilojoules. So, I told you that temperature would matter when the signs are the same, and it clearly does, right? Delta H1 at low temps, delta S1 at high temps. Now, let's say you were asked this question. Which temperature would result in the production of the most ammonia? Which one is spontaneous in the direction of ammonia? Ammonia is a product, so you need the temperature in which it's spontaneous in the forward direction, which means 25 degrees Celsius, right? Now, and this isn't on the slide, but let's try to figure out the temperature at which it swaps. Okay, so what temperature, because it's got to be in between 25 degrees Celsius and 500 that it swaps. So let's find that temperature, okay? So again, whenever you want to figure out the temperature at which it swaps, you're going to put a 0 for delta G, right? Is equal to, same delta H, 92.38 kilojoules. We're going to put an X here for the temperature. And then we're going to put in our delta S, negative 0.1984 kilojoules per Kelvin. Okay. All right. So then we're going to get 92, because it's going to be plus 92.38 on both sides. So 92.38 kilojoules is equal to a negative times a negative is a positive. So 0.1984 kilojoule per Kelvin, right? Hopefully, it would be a huge red flag to you if you ever got a negative number for X here. Because remember, X is a temperature in Kelvin. There is no such thing as negative temperatures in Kelvin. So you cannot get a negative number here. All right, but let's see what our number is going to be. 92.38 divided by 0.1984. And I get that X is equal to about 465.6, so you're going to want to round that up to 466 Kelvin. So that's the temperature at which you would want to flip it. And again, we could check that. So negative 92.38 minus 466 times negative 0.1984. And I get, well, a slightly positive number, which means you would actually want to take that and round that up. Well, actually, no, we went from negative to positive, so that is correct. Right, so 466 Kelvin would be the temperature at which we flip signs. All right, so that's it for today's lecture. We are going to pick up with this slide and how we can measure these different types of things when the numbers aren't directly given to you. Next lecture on Monday. All right, but we're done for today's lecture. Stover out.